Okay, good morning to everyone. It's a pleasure to introduce Dr. Manuel Solano Altamirano from the Facultad de Ciencias Químicas at the Benemérita Universidad Autónoma de Puebla, the Meritorious Autonomous University of Puebla from Mexico. And Manuel is a very close colleague. We were discussing a lot, actually, with many people in this session of the webinar, I guess. And let me say only a few words about Manuel. He is a multidisciplinary guy, so he has been interested in a very broad how to say in a very broad sense in a lot of very different problems. He is interested in protein folding, applying some novel methods to study the problem. He is also interested in thermochemistry and theoretical prediction of thermochemistry and in information theoretic issues about molecules and atoms. So he has recently studied the problem of two linked atoms, which we call a diatomic molecule. That is what he will be talking about today. So please, Manuel, the microphone is yours.
Thanks, Humberto, for the very kind presentation. Yes, I'm gonna share my screen. Please let me know if everyone can see it.
Yes, we can see it.
Okay. Thanks. Well, yes, thanks again. I'm going to start or talk with that special thanks to the organizers, to everyone. Humberto, Dr. Humberto Luna, Dr. Robin Sagar, Dr. Alejandro, Dr. Rodolfo Esquivel, and then Dr. Adrian Escobar. Sorry, I only have pictures of the first three and the other. I'm sorry for that, but well, I thank you as well. And well, today we are essentially be talking about very recent work that we published a couple of months ago, and it was published by these our colleagues, our team, Saúl Salazar, José Antonio, Humberto, Julio, and Robin, and obviously myself. This is the title of the talk as well as the paper. So it's going to we are going to talk about paired density Shannon information measures and their independent behavior in the diatomic molecular systems. For those who are interested in seeing the contents of the talk, well, we'll be talking about a very small summary of many electron systems, how to obtain one electron and two electron densities, as well as their representations in momentum space, and some basic definitions of information theoretical measures, a bit of details of how to integrate these information measures over the atomic over domains that contains the atomic molecules. And finally, I will talk about some results, and I'll close it with some conclusions and a few open problems. So we, as chemists, theoretical chemists, are very interested in solving the Schrödinger equation for a molecule of n electrons and m nuclei in general. In this talk, we will be constrained to talk about the atomic, only two nuclei. But in general, we are interested in solving somehow for any molecule of any number of nuclei. As you very well know, the most difficult part or the root of our nightmares is actually this term marked in red. Can you see my pointer?
Yes.
Yes, yes,
Okay,
yes.
nice. Okay,
We can see it. Yeah.
Cool. So this red term, which is the electron-electron repulsion, is, as I was saying, the root of all of our nightmares, because this makes very, very hard to use the separation of variables to solve this equation. And we solved it. The people obviously is very clever, and then for a long time we have been using the Hartree-Fock method. But in this method, we use several approximations. First, any relativistic effect is ignored. We are not really considering anything about special relativity. We also use the linear combination of atomic orbitals, in which the wave function is expanded as a sum of atomic orbitals, and each atomic orbital in turn is assumed to be separable as the direct simple product of single electron atomic orbitals, which is, if we think of a problem of many particles, this actually is very poses a lot of constraints, since from the beginning, as we are introducing kind of a separation of the electron-electron or two-electron contributions. Eventually, we can write them approximately, but again, is a product of single electron. But surprisingly, this approximation has been very successful, and is very, very popular. And in fact, everything we are going to talk about today will be using this Hartree-Fock method for solving the Schrödinger equation. Also, in the Hartree-Fock method, we use a mean field approach to include electron-electron repulsion. That, in simple terms, this implies that an electron will be moving within a field computed as an average of the rest of the electrons. Also, another approximation is that in practice, most of the popular software packages for solving the Schrödinger equation for molecules use Gaussian type orbital basis sets, which also have some peculiarities or cause some problems, especially the cusp conditions at the nuclei is not very well met, because, well, we know for hydrogenic atoms, the electron density near the nucleus should be closer to Slater type functions and not to the Gaussian functions. So this kind of introduces another numerical error. But then again, it's very popular because electron-electron integrals and other integrals are very, very fast to solve. So this is a popular choice by excellence. Finally, antisymmetry of the wave function is accounted for through a Slater determinant. And let me advance a bit. The use of Slater determinants accounts for exchange correlation between parallel spins. But not every correlation, electron correlation, is accounted for through this method. Furthermore, well, this is the expression just to remember a bit of the how is written Slater determinant, which is basically an antisymmetric combination of electron position and the single electron atomic orbitals. Furthermore, we use a variational approach, which means that we only consider the energy for solving the Schrödinger equation. We do not really have many boundary conditions for the wave function, except that it should be zero as at large distances and possibly the cusp condition, but we cannot really use the boundary conditions for solving the Schrödinger equation. Instead, we use the variational approach. And that limits us to only consider the energy, which is not a bad thing per se, but it's another approximation when we solve the Schrödinger equation. Also, we traditionally integrate over spins. After averaging out the spins, we obtain the one electron probability density. And frequently, also, we have these two views, two ways of doing things. In the, I don't know, when informational theory was first applied by chemists, they used the n-normalized electron density. That is, if we integrate the electron density overall space, then we get the number of electrons. But recently, in the, I don't know, maybe 15 years or so, the chemical community started to shift to use or prefer to use the the electron density normalized to 1. And well, we can get the electron density normalized to 1 by simply dividing by the number of electrons. Throughout all this talk, if we see a hat inside of a quantity, that means that we are intrinsically using the n-normalized electron density. And if it appears without the hat, is assumed to be using, or the density is assumed to integrate to 1. Now, when we solve the Schrödinger equation through a chemistry software such as Gaussian, Orca, Nuchem, or any of these packages, we can request to the program to give us the wave function. In simple terms, the information that we get from the program is actually a set of coefficients that are related to molecular orbitals, and each molecular, or sorry, again, this is not even molecular orbital, actually is it's molecular but single electron, or at most 2 electrons, depending on how we set up the system. And but anyway, let's assume for a moment that we can split always the orbitals, and always the number of the occupation numbers, which are these Cm, are going to be between 0 and 1. Now, if we use Hartree-Fock to solve the Schrödinger equation, Cm will be either 0 or 1. There is no middle or fractionary numbers. But if we use another more refined methods, such as, I don't know, Moller-Plesset or coupled cluster configuration interaction, then we would obtain natural orbitals that may have occupation number fractionary or fractional occupation numbers, that is numbers between 0 and 1 and of any value. But I will touch this later, but this poses other problems. In this talk, we will be constrained or only referring to Hartree-Fock method, so our occupation numbers will be 0, 1, or at most 2, but as special cases, that is when we put up to 2 electrons in the same spatial orbital, and the only difference between the 2 electrons is the spin. Furthermore, each single or 2 electron molecular orbital is expanded as a sum of usually Gaussian type orbitals, called also primitives, and each primitive will be given, or will have this mathematical form, which essentially is an angular part and an exponential factor. And here is the root of the name, is the Gaussian. This is a Gaussian function. Each primitive is going to be centered at certain nuclei, And here we get away a little bit from traditional naming or indexing system, and we prefer to use these 8 dots to easily identify several things, like this index runs from 1 to m, this from 1 dot to p dot, and it's supposed to be easier to identify which index runs for all the molecular orbitals and which index runs from the primitives. This expression, the sum of all these coefficients at the end of the day, can be shortly expressed as a matrix, which we call density matrix from a computational viewpoint. And if we use Einstein's summation convention, then we can write very compactly this very long expression. Now, this is the expression that we'll be using in our program. We in the laboratory have developed a program to first compute these functionals and any other density function derived from expressions like this. Now, there is some caveats that I will be discussing a bit. All these coefficients, the expansions in molecular orbitals, are computed internally by programs, the chemistry software, Gaussian. I will talk about Gaussian just as an example, but any NWChem or Orca is the same. Any package will compute the wave function, that is, it will compute these coefficients by first reducing the wave function, the complete wave function, by integrating and computing the reduced density matrix of order 1. And essentially, this is the expression which consists on integrating over all the electron coordinates except 1. And furthermore, we put a prime coordinate. In this way, we have 6-dimensional density, which can as well have the relevant information related to the correlation. But again, after the program gives all these coefficients, we have, or we can write the reduced density matrix of order 1 in this simple form. Again, unless stated otherwise, here we are assuming the Einstein convention. And this property, if we set R1 equal to R2, then we get straightforward the electron density. That's a feature. Notice that we are so far we haven't been able to get the reduced density matrix of order 2, which would be important if we can we want to compute 2 electron densities. And we have the problem that we have to reconstruct a 2 electron density starting from essentially 1 electron properties. So there are 2 approaches we know, but well, I am just saying this as a thing that we will touch later in the discussion, because we are reconstructing 2 electron densities starting from 1 electron densities. Even if apparently we have 2 electrons here, at the end of the day it comes from the same position. Just mathematically we trick it to make it appear like 2 electrons, which is better than nothing, but it is not the most exact two electron density or function that we can have by averaging out the rest of the electron coordinates. Now, electron density can be interpreted as the probability of finding an electron of any spin at the position R. Here in this talk, we will not be making any difference, or we will not take into account the specific spin of each electron. We just get the probability of finding any electron with any spin at certain position. And that is the information that we get from the electron density. But what about the two electron probability? That is the probability of finding an electron of any spin at R1, provided that another electron is also of any spin at R2. We denote this quantity as gamma uppercase of this of R1 and R2. This is supposed to be a real two electron function or six-dimensional function. Well, as I was saying, we can recover or construct the two electron density starting from the electron density and the reduced density matrix of order 1. For closed shell systems, this is the expression. And well, it's a bit easier to write it using the n normalized electron densities, but then again, we can rewrite this in electron densities normalized to 1. This term, together with the constants, etc., maybe usually it's thought as an exchange density function. And that's information that we'll use later. Now, so far, I've been touching about the probability of finding an electron of any speed at position R, but one can also ask for the probability of finding or an electron having a momentum p, which we denote that function as pi of p. And it is obtained through Fourier transforms of the wave functions first. First, we obtain the Fourier transform of the wave function, and then we, in principle, use the same method to obtain the coefficients, but after all the math, the expressions or the coefficients do not change. And the only thing that changes is that instead of using the primitives in the position space, our electron density in momentum space will be obtained by simply replacing the primitives by the Fourier their Fourier transforms, which every times we get this tilde, then we imply that we are using the function in the momentum or the transform of the primitive or the function. For instance, we can also get the reduced density matrix of order 1 in momentum space, and that also is given by this expression, very similar to the other one. And the two electron momentum density has essentially the same expression, just changing the electron densities in position space, but their Fourier transforms. Now, as I was okay, now I will talk about our main concern in this work. That is how we can address this red term that we have here. If we try to include more information about how one electron is affected by the rest of the electrons, then we should consider in principle all the electrons, but then again we are under the Hartree-Fock approximation, so the effect of the rest of the electrons is averaged. So there are the I guess the most fundamental question that we can ask in this is to what extent this approximation is good, to what extent all the electrons affect another, and then that is the thing that we know very roughly as electron correlation. That is how one position is affected by the others. And then the most interesting question, or the question that underlies this work, is how to measure the electron correlation. We know that mean field approximation captures some electron correlation, not all the correlation. It only captures the correlation stemming from the exchange, but not other effects. For that, more refined methods have been developed, like post-Hartree-Fock methods. But again, how to measure this electron correlation? Well, we can ask the same question in another form. That is, to what extent the two electron density function is exactly equal to the direct product of the one electron densities. If we pose the problem as this question, then we can, in principle, ask or obtain the answer by checking if the two electron is exactly the simple product of the one electron densities. And this condition should be accomplished for every pair of coordinates. If we found that, then we can say the two electron density is or the electrons are uncorrelated. And the same for momentum, in that case not position, but the two electron momentums are not correlated if it's the direct product of the one electron densities. But let's think about the problem. It's not a bit difficult, it's actually very difficult to measure or study the two electron density because it's a 6-dimensional function. So we don't really have very easy methods to study it. Especially visually, I'm thinking on visual terms, because we have a 6-dimensional function and then we would need to plot somehow information in 7 dimensions, which is very difficult. The most complex thing we can plot is a 4-dimensional thing, but let's say a function of 3 coordinates. But it is simply impossible for us to study these two electron densities using this approach that is checking at each pair whether this equality accomplishes or not. So fortunately, I guess we are all here because we know and we like that information theory provides a measure. Either Shannon entropy is the most simple form, to determine the average uncertainty and predictability or surprise inherent in a set of possible outcomes or data values. In a simplified manner, Shannon entropy may tell us how different a distribution is from a constant probability function. And that is the most, let's say, basic, simple way of measuring whether this is correlated or not. But the informational theoretical theory, the informational theory provides as well measures to determine how different two arbitrary distributions are between them, which is actually, I guess, more useful. And I am not diminishing the importance of the Shannon entropy, but we will have information, this especially we will take it about later, but I am thinking on mutual information that, or the Kullback-Leibler measures that are measured specifically designed to compared to densities or distribution. As just history, I am putting here the one electron Shannon entropies in position and momentum spaces. And that is very simple, is the distribution log, the same distribution integrated over the whole space with a negative sign. And then we get the entropy or the Shannon entropy. Also, one of the interesting things or properties these Shannon entropies applications is that the uncertainty principle, Heisenberg uncertainty principle, can be formulated as using the entropies. And very shortly, this can be stated as follows: the sum of the entropies in position and momentum spaces must be always greater or equal than this number, 3 times 1 plus logarithm of pi. And this is a lower bound, the number, this is a lower bound for the three-dimensional functions. And this accounts underlyingly for the Heisenberg uncertainty principle. And this has been known for some time. This is for the one electron densities, and if we use or study two electron entropies, density distributions, then we can also compute the two electron Shannon entropies as well in position and momentum spaces. Basically, they have the same form, the distribution times logarithm of the distribution integrated over the whole space. In this case, we have, this should be R1 and R2. But it is the whole space and six-dimensional space. There is a similar entropic formulation of the uncertainty principle, and the difference is between the previous one is that we will have a 6 instead of a 3. This number usually reflects the dimensionality of the problem. And this measure tells us as well how different is the two electron density function from a constant distribution. As I commented in the beginning, not in the beginning, a few slides ago, we fortunately have this more specific measure that determine how much in this case specifically, how much the two electron density is correlated, or how big is this difference, how the two electron density is gets away from the direct product of the one electron densities. And then we computed like this, using several properties of the two electron density. Then we can show that this is reduced to 2 times the one electron density minus the two electron Shannon entropy. And this difference must be greater or equal than 0. And we can define the same or similar measure in momentum space. This is possibly the most sophisticated measure that we will use here for measuring how different or how a wave gets the two electron density from the product. Or this, in other terms, if this is greater than 0, then we can say that the two electron density is not correlated, is correlated. Sorry. Now, the problem that, or the novelty we are discussing in the paper and in this talk, is that it is relatively simple to compute these properties in single atom systems, because we can use numerical quadratures, Gaussian Gauss quadratures, for integrating them in spherical domains. But the problem is that if we have two nuclei, then it becomes a bit difficult to integrate these functions. And for that, we developed a scheme to integrate the atomic molecules. In very rough terms, we determine a sphere that is large enough to enclosure the two nuclei, and by large enough, we mean that if we compute the electron density at the boundary of the spheres, we will have this property, that it will be the electron density numerically will have a value less or equal than 10 to the minus 14 atomic units. Why this? Well, this is just empirical. We found that even if we determine a sphere in which it is, let's say, 10 to the minus 12, then we will get numerical errors. So this is empirical, but it worked. And then after determining that spherical shell or boundary, imaginary boundary, we make a change of coordinates and split the problems in first integrate the property, in this case, the electron density or any other function such as the product log rho or rho log rho or gamma log anything. We integrated over one sphere, a small sphere that has a random radius of approximately 0.75 the van der Waals radius of the atom in question. And the same for the other atom. And the rest of the domain, we integrated it using this change of coordinates. More details, you can find that in this reference. But to be honest, we haven't published the complete details. We intend to release later as a library for anyone to use. For now, it is included in our developed version of our programs. But well, we found that this decomposition gives us the possibility of computing any three-dimensional function with accuracies, with high accuracies. Usually we can have relative accuracies of 10 to the minus 8, 10 to the minus 6, relatively easy or cheaply, computationally speaking, for the atomic molecules, which enables us to compute the pair Shannon entropies with numerical certainty. And that is the scheme we are using in this in the results I am going to talk about. Now, we studied more the atomic series, two series. One is what we call a homonuclear series or XX series, in which, well, we simply construct the atomic molecules of the same atom. And in this sense, well, informational entropies of atoms and the atomic molecules in three-dimensional or one electron informational entropies have been known for some time. I give you here some references. But there is not much information about two electron informational measures for the atomic molecules. There are information for two electron informational measures for single atoms and for schemes usually more not complex in the sense of these Gaussian type expansions, but other simpler atomic orbitals. Very nice approximations, by the way, but in terms of the computational cost and computational development, these quantities, the two electron informational measures, have been computed for very few systems, mainly atoms. So that is the novelty of our work, because we can compute the two electron Shannon entropies of two atom molecules. So the main question here is what are the two electron informational measures of the atomic and possibly polyatomic molecules? Well, that is what we are presenting. And then these are the first results. We are here comparing the two electron Shannon entropy in position space, in momentum space, and the sum of entropies. And we compare directly with the same information, but for the one electron entropies. These are the one electron entropies in a very well-known paper by Minui Ho, published in 1994. They have similar shapes, or one of the things that we can say is that the n dependence here with the atomic number or the number of electrons equivalently retains or reflects the atomic structure of the periodic table. And we kind of say the same in our case. There is some structure reflected by or kept some structure that reflects somehow the structure of the periodic table as well. If we compare it, they have similar shapes in every property. But here I must say, here I am presenting the entropies computed with electron densities normalized to 1. If we compare directly with the the entropies computed with the n normalized electron densities, then the structure remains only in the position space, but it is not exactly seen equivalent or similar to the in the other, the momentum and the sum of the entropies. But well, I don't know if this is very important, but what we will be presenting in the rest of the talk, we will always be talking about the entropies obtained with the electron densities normalized to 1, or the pair densities normalized to 1 as well. And here are one of the things that we get in or publish in the paper, that is how the two electron entropies behaves as a function of different basis sets. In previous work, it has been shown or stated that the Shannon entropies in one electron Shannon entropies can be used to measure the quality of the basis function used. We computed for the two electron entropies for this series, and well, we can say a similar conclusion, that using bigger basis sets relative to the STO3G makes the Shannon entropies in position and the sums to increase as a general trend. This would be the for this here at the left, I am showing the dependence of the Shannon entropy, the respective Shannon entropy as a function of the number atomic of the atom in the diatomic molecule. And the dependence on the basis is, I guess, best shown here, that in which we measure the difference between the entropy computed with a certain basis minus the same entropy computed with the STO3G basis. So as a general trend, we can say that using a bigger basis than STO3G renders the bigger or greater entropy, Shannon entropy, in position and in the sums. but the opposite trend is seen in the momentum space, in which the entropy decreases if we increase the basis. Apparently, there is a limit on how much correlation can be captured by simply increasing the basis set. Because if we measure this, all the differences are similar. So after we set to the basis 3 to 1, actually in some cases it seems to improve it better, we do not really gain that much correlation. Again, as measured by simply observing the changes in the Shannon entropies. The Another observation that we have is that the some of the entropies respect or follows the lower bound we show with the previous slide when we were talking about uncertainty principle. This is the numerical value, and we see that we always have even for the HH system, this number is greater. It's approximately 13, which is greater than this number, and is bigger for any other system. Also, the entropy sum increase with the number of electrons. The number of electrons should be twice this number. So that is the main observations we can get from the pair entropies. And as to the informational the mutual information, which again tells us how much the pair density function gets away from the direct product of one electron densities. In general, we get these results that the mutual information is greater than in position space, is greater than the mutual information in position space. Well, like this we can get by comparing point by point. But well, it can be shown better in tables. In the paper, we actually did not present these plots. We presented the tables to compare directly, but I guess in a presentation it's easier to show this here. And another, well, the interpretation of this is that the exchange component, this term in the original definitions, here, this would be the exchange term, is relatively larger in position space. That is our interpretation. So there are more correlation in position space than in momentum space. Another trend is that say for the HH molecule, both the mutual informations in position and momentum spaces decrease with the number of electrons. Again, this n is the atomic number in the molecule, so the number of electrons is 2 times this n. This is as a general trend, it diminishes, both diminish as the number of electrons increases, but there seems to be a local maxima around the magnesium, the MgMg molecule. We don't really know if this is a true minimum or not, but we will possibly left it as an open problem. Also, we see that increasing the basis changes the mutual information, but it improves or worsens the electron correlation depending on the system. That is, we do not really have a clear trend. We can say that if we increase the basis, we get a bigger or larger mutual information. In some cases, it worsens. So in this sense, we could even say that increasing the basis decrease a bit the correlation. But this information is new, and it is, I guess, in contraposition of what it has been said, always only looking at the pair Shannon entropies, in which usually it is said that increasing the basis you will get a better uh, or increase the quality of the wave function. But using well, it's not exactly in contraposition, but it is not exactly clear because the mutual information would be measuring the how much the pair distribution function is correlated or not. So, well, we have these numbers, and I think that is new information. Not increasing the basis will not always, or simply increasing the basis will not better, will not cause an improved correlation, not because of the basis. We studied a second diatomic series in which we fixed a hydrogen atom and we varied the second atom. And in the plots here, we will be using N as the atomic number of X in the diatomic molecule HX. We have similar shapes, relatively similar shapes as those we have in the homonuclear series, and obviously it's also relatively similar to what we observe in atoms. And the conclusions are very similar, using bigger basis sets relative to the STO3G. Makes the Shannon entropy in the position and the sum of entropies to increase as a general trend, and bigger basis sets decrease the pair entropy in momentum space. We can again see these trends here more clearly. The differences are positive for S total, except for these tiny points here around the beryllium. Or lithium, I think. Lithium, in which actually worsens slightly using a bigger basis set. Well, but as a general trend, usually using a bigger basis sets cause an increase in the sum and decrease in the momentum space Shannon entropy. Mutual informations, again, we get essentially the same trends, but in this case, we have kind of two local minima around the beryllium and magnesium molecules. By the way, for many of these diatomic functions, we used experimental distances to compute them. And well, it is not very clear if these maxima or what are the causes of these maxima apparently seen here. But well, another conclusion is that increasing the basis not necessarily improves the electron correlation. And this is also similar to what we observed for the XX series. Now, this is so far I have presented the information or quantities that are, let's say, new because they haven't been published before, because essentially the difficulty in integrating the functions in six-dimensional spaces. But we in the paper also found or published a couple, well, not three other dependencies or fits that we thought were very interesting. In previous work, Shannon entropies were, let's say, fitted to equations, and in that manner, let's say the entropies were shown to follow certain simple equation forms. The simpler is the one given by Gadre, and that is the Shannon entropy is proportional. Well, it has this form, a linear form, plotted against the logarithm of the number of electrons. There is another relation with the first ionization potential of the molecule and has this shape. And the third one is that the group of Professor Robin, in this case, but Saul Salazar, um, found general expression for the problem of n interacting one-dimensional harmonic oscillators. And they found that this is the entropies, the sum of entropies have this form for that system. K here represents whether is the n interacting. So, we have n harmonic oscillators interacting somehow, and that somehow will be given by this parameter lambda. And they found that, well, this omega is the intensity of the body harmonic potential, and this lambda uppercase is this expression. And again, lambda lowercase has information on how strongly coupled are the harmonic oscillators. Now, for adapting this equation to our systems, and that is the most interesting thing, is that even if this is an expression for harmonic oscillators, if we make these substitutions, we replace omega by the number of electrons to the alpha, to the alpha power, which intuitively accounts for the effective nuclear charge effects and in an attractive potential. And we also use positive values of lambda. This choice is only made for because that improves the fits. And we set k equals to 1 for 1 electron. When we talk about 1 electron informational measures, then we set k to 1. And if we talk or compute properties of 2 electron functions, then we set this k to 2. And if we apply this, well, we can shown in the paper that we can actually get a closed form of the mutual information, and it has this form. We do not have this any similar for the other models. In principle, it should be possible to do it, but what we found is that the fittings behaves as follows. The Shannon here in this case, if you see lowercase t, is because we are talking about the sum of the 1 electron Shannon entropies. If you see the uppercase t, then we are talking about the sum of 2 electron entropies, and this would be the mutual information. Obviously, this includes 1 and 2 electron densities. The fits are qualitatively okay for the simpler form that have been used in atoms. Qualitatively, the most interesting thing we found is that the expression contained in the first ionization potential fits qualitatively very, very well to both the entropies in the 1 electron entropies as well as the 2 electron entropies. But neither of these expressions fits qualitatively okay for the mutual informations. In fact, this is very qualitatively is not very nice. On the other hand, these models stemming from harmonic oscillators, coupled harmonic oscillators, we found that yes, they qualitatively also fit very nice the trends. And sorry, here I am talking about neutral atoms. We did not show the pair entropies or anything like that because they were published previously, essentially, and then we only the novel thing in the paper is that we found these correlations for the atom series. But then again, we found this interesting fittings. But the best or the most interesting thing is that the mutual information couples qualitatively very nice to this model, even if it's again a model stemming from harmonic oscillators, uh, which cannot be said about the other two models. So if we repeat the process for the homonuclear diatomic series, we found as well qualitatively the best approach or the best model for fitting the data about the 1 and 2 electron Shannon entropies is the model that includes the first ionization potential, and the best model for fitting the mutual information is the harmonic oscillator. The harmonic oscillator also fits relatively well the Shannon entropies. So I don't know. I guess this could be seen as the most complete, in some sense, model because it captures very well all the three measures, but qualitatively, this is the best method for the Shannon entropies. The model that includes the ionization potential. And for the XX series, the again is the same conclusions as well. The first ionization potential model captures very well the trends and jumps observed in the entropies, but again, these models do not capture the shape of the trends seen for the mutual information. This model captures it sufficiently well, though it cannot, let's say, capture these small jumps that we can identify as possible local minima, so maxima. But overall, it is still the best model that captures the information or the data. Here I just left this for reference. We computed the adjusted correlation coefficients and the archaic information criterion, and this coefficient is to be interpreted as the smaller value that includes the more negative value, then the better the fit is. So these are only numbers that confirms what we discussed here heuristically, because well, usually here the larger correlations or the smaller numbers for the archaic information criterion are for the homonuclear, and essentially always the biggest values are found for the mutual information. And even if we have not very clear correlation coefficients. Sorry, this is for what was I saying? This is for the correlation coefficients for the fitting of to the simpler model. This is for the first ionization potential model, and this is for the harmonic oscillator models. But well, again, it's only numbers, and I left only as reference. Well, finally, I will close with some summary that is from what we saw, and that is using bigger basis sets relative to STO3G makes the Shannon entropies, pair Shannon entropies in in position space, and the sum of entropies to increase, and the Shannon entropy decreases. The mutual information is usually larger than in the position space is larger than the one in momentum space for all system, except for some small differences. The X, well, if we compare homonuclear series against the heteronuclear series, then the heteronuclear series have smaller differences. Usually, both the mutual information in position and momentum space decrease with the number of electrons as a general trend, but there seems to be local maxima of the mutual information in position space around molecules with atoms beryllium and magnesium. Also, increasing the basis not necessarily improves the electron correlation measured through the mutual information for the atomic molecules. The pair entropy sums fit best, especially in qualitative manner, to an equation of a form that includes the first ionization potential, and the pair entropy sums fit well, not as well qualitatively as the model for the fish with the ionization potential, but fits sufficiently well to equations of a form found for the harmonic oscillators. And mutual information measure fits best to the expression that correspond to the harmonic oscillators. That is as a general trend. Some open problems that we are working now is to study other informational measures such as Jensen-Shannon, Jensen-Salis, Jensen-Range divergences, also quantum similarity indices. I think we have it is not very difficult to implement these measures since we have already the integration algorithms for the atomic molecules. And everything that we have studied today is also now, we're working now that for polyatomic molecules. We have now an integrator that can integrate two electron informational measures in polyatomic molecules. And now I guess we are working in the future, we will have some more results to present about molecules with more than two atoms. Also, the problem that we have open is how to use wave functions with more than one Slater determinant. That is how to compute two electron densities when we have or when we solve the Schrödinger equation using post-Hartröpke methods. If we have more than Slater determinant for that, then these expressions should be possibly different because, let's say again, this two electron density is reconstructed using one electron density. Especially this term is not clear how to recover or to construct, whether it's even correct to construct multi-determinant wave function using these expressions or similar expressions for the open shell systems. So that is an open problem. That's an open problem. We are working on it. But well, that problem, I guess it will take more time to solve. And well, many thanks. And also we need to mention the funding de Ciencia y la Secretaría de Ciencia y Tecnología, Humanidades e Innovación, and also the Laboratorio Nacional de Cómputo de Alto Desempeño de la UAM, de la Universidad Autónoma Metropolitana. Well, thanks.
Thank you, Manuel. So we have time for questions, comments, and you can just raise your hand or simply open your microphone and ask directly the question.
I have a couple of questions. I don't know if
No, yes, you can start. Yes, Alejandro, please. Yeah, please.
Okay. Thank you, Adrian. Thank you, Manuel. Very nice talk. I understood a lot, which is non-trivial for me being non-trivial and expert on these approaches for the atomic systems. My first question is related with this increase on the basis. You were talking about enlarging the basis and And what I appreciate is that somehow the behavior fluctuates. It's not really steady for some of the measures, in particular for the first one, right?
Yeah.
Yeah, can you expand on this, because it's like the effect is really like problematic whenever you increase the size of the basis set. And I wonder
Yes.
what do you think about this, if you can expand on this.
The thing that we know is that there is an inherent problem. When we increase the basis set, for instance, the 631G, then first, if we are talking about the hydrogen, then you almost add anything. You get the same basis. Then the programs, the quantum chemistry programs, start to add atomic functions, but they add it by rows of the periodic table. That is, if you add certain number of bases by the whole row. So you are not really increasing the bases according to the atom, but the row. And I guess that's a possible problem because you are not really, you increase it like in jumps.
Okay.
Right? Even the same increase, or if you jump to the third row of the periodic table, then you are using, in fact, more bases. Even with the same keyword, you're using usually more bases for the third row than the second. So in reality, you are not really increasing the basis proportionally to the atomic number. You increase it by jumps. So eventually, if you are, let's say, piling up electrons, then you are using more of the basis, roughly speaking, than for the first atoms of the row. For the first atoms of the row, you have more orbitals where to put the electrons. So I guess that could be a possible source. And
of the fluctuation.
yeah, eventually you are using the 2s orbital. Then you start to using the 2p orbital. So in fact, you're accommodating electrons in the 2p orbitals, as opposed to the first, the alkali atoms. So I guess that is possibly one of the causes, but I really, really not, no, we're not really sure. Perhaps these studies are a bit inconclusive because, again, we are not really increasing the number of bases according to the atomic number.
Yeah, it seems that whenever you fix the system, then you can play with these different bases. And at the end, it seems that you don't reach a point at which you really say the system has stabilized, and then I do have the correct basis for describing the system I want. So it's like you have to play with different bases and then do these calculations with all of them, and then have to play with all of these results together instead of having one particular way of describing the system.
Yep. But that is, again, because we are using the same basis set for a whole row. So people usually do that. And well, I haven't thought of this in that way, but maybe this is telling us that we actually need to improve the basis in, let's say, specifying a basis per atom. One basis specifically for each atom, not for each row, right? If we are interested in improving the electron correlation, of course. For other things, maybe it's enough. But if we want to increase the electron correlation, perhaps we need to adapt a specific basis for each atom.
Maybe they are not universal in the sense that you want a basis that works for all the atoms, but instead of that, what you're having is that no, maybe you have to work with basis for particular atoms instead.
Yeah.
Okay. My second question, I don't know if I I continue with my questions, Adrian and Manuel?
Yes.
Yeah, okay.
But at the end, yes. Yeah.
It's this is Shannon entropy, right? And but then my question is, what these results tell us about what Shannon entropy is?
Well,
I mean,
that's, I guess,
we calculate Shannon entropy as a measure of the information and the uncertainty, and in certain cases, it can be interpreted as the whenever you work with the sum of the Shannon entropies for position and momentum, we can say something about uncertainty, entropic uncertainty relation. But still, one question might be like, okay, but at the end, what is the Shannon entropy? Is it's really an entropy, and then I wonder whether this result can shed some light on approaching to the truth behind the concept of what Shannon entropy is. And I don't know if you have thoughts on this.
we have thought in the group, we have discussed that a lot because that borders on the philosophical part of the Shannon entropy. One thing I commented is that we are using the variational entropy, right, for solving the Schrodinger equation. And in this variational entropy, we're only considering the energy. So one of the things I have been trying to convince my colleagues is that if we change these by kind of a first, second law, or kind of a Gibbs energy, in which you have energy and entropy multiplied by some stuff like temperature or something, maybe you can change the variational entropy by some other principle to compute this, because we are actually getting the ground state and wave function, but constrained to be only the let's say the expansion that gives us the lowest energy. But that doesn't mean that your system must be in the lowest or the ground state. So, but this is kind of here I would be thinking of the informational or Shannon entropy as similar as the thermodynamic entropy, that it gives us a measure of uncertainty and that we can use it for studying our systems. Now, how to interpret it? Well, again, my way of thinking about the Shannon entropy is that gives us a measure to say how a probability distribution function gets away from the constant distribution function. And
but that works for discrete cases. For the continuum, that's really problematic.
yeah, it is still problematic. And again, that is more like I don't know, philosophy, like whether we can represent the space using R, the real numbers. If we say that the space can be divided in an infinite number of times, then we can represent using the real line. But if we consider that the space is quantized, then we could not really use the real numbers. So in this sense, it's the same. It is kind of these problems that I think they are open. We don't really know how to interpret it for sure. We have several interpretations, several ways of thinking, but I don't think there is a conclusive or one unique manner to think about the Shannon entropy. But well, my colleagues maybe contribute on that because they are more expert than me. I am still on the border.
Yeah, my interest is related with the fact that you increase the number of electrons in your system, right? You have HH, then I think helium, I don't know, lithium, so on and so forth. So you are increasing the number of electrons in your system, and an open problem. You mentioned open problems, and an open problem is the semi-classical or the classical limit of quantum mechanics. And then the core of my question is whether these approaches can help physicists, philosophers to explain what the classical limit of quantum mechanics is by using these results, for example, and whether at what point, for example, the uncertainty principle is no longer a principle, and it's no longer a principle in the sense that the H bar goes to zero somehow, right, as an effective behavior. And that's the core of my questions. And the last one, I don't know if you want to mention something about that.
I guess that is a very interesting question, but here we must not forget that yes, we are increasing the number of electrons, but we are also changing the effective potential in which the electrons are moving, because we are actually changing the nuclear charge.
Yeah.
So in that way, we are not really making perhaps a fair comparison. Perhaps the fairest comparison should be using the same potential and increasing the number of electrons. In this case, it is, although we are presenting this information in this manner, we inherently are changing the potential, the nuclear potential for each system as we increase the number of electrons.
Yeah, you're taking larger, different atoms every time, right?
And yep. So
that's
we are not
potentially changing.
Yep. So we have actually two things changing here. And other studies have also, let's say, fixed the potential and then increase the number of electrons using the same nuclear charge, or changing the nuclear charge with the same number of electrons. And they have also trends. So it's a bit difficult to separate these two things. It's not as simple as increasing the number of electrons, but also changing the potential, right?
Okay. Maybe this is the right way of doing this classical limit, changing both.
Yeah.
Okay. Thank you, Manuel.
On the contrary.
Thank you, Alejandro. More questions?
Hello.
Hi. Hi. Please, Shantano or Ravena, it's up to you. Yeah, you can.
Yeah, Ravina, go ahead.
Yeah.
Okay. So my question is, when we are calculating mutual information, so it is for calculating the correlation part. Is it? I am understanding right or not?
Yes, somehow
Yes,
it's
yes,
a
yes.
number that gives us how much the two electron density gets away from the simple product or direct product. This is when electrons are not correlated, is that the one electron will have the same probability independently of where a second electron is. So if these were zero, if this equality holds, then the mutual information would be zero.
So when we are calculating this, so can we distinguish the Hartree-Fock result or correlation result, or we will get the adding the total?
No, it's not that simple, because we obtain this two electron density and it is a sum. Here we have, let's say, this would be the Hartree-Fock, and this would be the product, and then this would be the exchange. But this term is obtained from a Hartree-Fock wave function. So this only tells us about the exchange of electrons, and it is a sum here, so we cannot really separate that, because this logarithm will have also a sum, so we cannot actually decompose in two parts.
Oh,
I don't know if
so we can't distinguish the result between the only Hartree-Fock and correlation part. We will get the total. That is the answer.
Yeah. Sorry, again, can you?
I am saying that when we will get the mutual information, so we can't distinguish the Hartree-Fock result.
Yes and no, because we can actually compute, in principle, if we would have the two electron information with another wave function obtaining with the other post-Hartree-Fock method, then we could actually just subtract the Hartree-Fock. In that case, we could identify what comes from the Hartree-Fock and what is not coming from the Hartree-Fock.
Similar as Hilary's method, I guess.
I guess, yeah. But in that case, if I will remember, then we have functions or primitives of two electrons, if I will remember. So in that case, you are not splitting or not making these direct products of the atomic orbitals into one electron. In that case, if I will remember, you have the two electron. Your wave function is constructed using, from the beginning, two electron orbitals.
Yeah. So my question is, as this is the wave function method, so this method will give the benchmark results if we proceed.
Yeah, that is I guess is the most the lowest bound, possibly, and the less correlated, right? Because other methods will have, in principle, more correlation, electron correlation. So this, yes, should constitute the lowest bounds.
Okay. So we can deal with any atomic or molecular system with this method.
Yes, in principle. The problem is not in the wave function, is in the how to integrate these the two electron densities. But now we actually can, well, in our research group, we now have the tools for making these integrations. Actually, we have, in principle, we could also extend it to any wave function obtained with any method. The problem in that case would be how to obtain these two electron densities. But, well, it's a yes and no answer, I guess.
Okay,
we have
so
the method to integrate it, and
yeah.
and we can obtain the two electron for Hartree-Fock. We are not sure if we are getting the two electron density function for post Hartree-Fock methods. So even if we can integrate it, we are not really sure if the results are correct. And we can extend our programs to include if you tell me how to compute the two electron functions, we can integrate it.
Okay, so now last question is, if we include any confinement effect by giving any external potential, so how mutual information will affect? That is my curiosity.
To be honest, I don't know. We actually, again, if we can, in principle, with this method, actually, we can confine systems, but, well, no, to be honest, I would be just speculating. I cannot answer that. We need to measure it and see the numbers. Perhaps my colleagues know more historic information, how confinement changed. I guess it would be having the same effect as increasing the nuclear charge with fixed number of electrons. Usually, I think the electrons are more localized, so your entropy in position space should decrease as well as the sum.
Yeah. Thank you, sir. Thank you. Done.
Thank you.
Hi, Professor Emmanuel. Thank you for the talk. So, okay. So I was thinking, I already had an idea from Ravina's questions, but I was thinking, since you were calculating some correlation, but it is based on the Hartree-Fock method, I was thinking you already know how to calculate the reduced density matrix, and also you have calculated correlated or two electron Shannon entropy or something. So it explicitly says something about the correlation. So I was thinking about whether is it possible, it has to be post-Hartree-Fock, I think, to calculate some entanglement entropy like von Neumann or something like that. Is it possible? Because you are doing with the wave function based method. So it will be really, really nice to see some real correlation with some real entropy like entanglement. Is it possible?
Again, in this case, if you tell me how to explicitly how to compute this two electron density function, if you give me the expression to compute it, then I can help you integrating it. That's the thing I can do. The problem is for post-Hartree-Fock methods, we are, even if we have an expression, we are not really sure that if you use more than one Slater determinant, you are getting the correct two electron density. Because again, it is kind of direct to reconstruct the density matrix.
But Professor, still we don't need the density. We need the reduced density matrix.
If it is
possible to,
okay.
If we have the reduced density matrix for that one, it is okay, and I know how to calculate the entanglement. Okay, is it possible to even?
Yeah. Do you have the density matrix of order 2?
Yes.
Okay, then that's all that we need, because in that case, if you have this reduced density matrix of order 2, the two electron density or the two particle density is getting only by, let's say, removing the primes.
Okay.
So in that case, if you have the second order reduced density matrix, the two electron density is simply get by remove the primes, and that is the correct way, or the best two electron the most real two electron density. And then we just plug it into our program, and then we can compute it.
Okay. So we can think about that. Thank
Great.
you.
That would be great.
Okay.
Thank you. Just one last question, because I was curious about what's the guiding principle when you explained the variables of integration. There is a group theoretical or symmetry based approach to select the coordinates. I didn't get quite well how.
Yeah, I did not really delve into it. Yes, if you in 3 dimensions, if you the atomic molecules, if you can say that they are azimutally symmetric, then you can actually reduce from 3 to 2 dimensions, and then you need to only integrate this function in 2 dimensions. But the thing is, if you are integrating the 2 electron densities, even if your 3-dimensionally symmetric system is symmetric, you cannot really use that property for integrating the 6-dimensional property, because you will have these R1, R2 distances that depends on the angle. Even if your density, one electron density, is symmetrical around the z-axis, you lose that, let's say, feature. You lose it. That advantage, you lose it when you're integrating the 6-dimensional function. So you have actually to also integrate around the azimuthal angle.
Okay.
Yeah, we can. Yeah, we try it, and we cannot get a cleverly bypass that problem. We need to integrate in 6 variables.
I see. No, it was related because Raven asked about this confining potentials, but also you cannot maybe, I don't know, magnetic field, electric field, whatever, and then it's important how we generalize the the approach. But yeah, it's
but in integrational numerical method, and that's one of the difficulties, because you cannot save integration points. And I'm talking about in numerical integration. You need yes or yes. You must use the 6-dimensional grid or mesh.
Right. Okay. Thank you, Manuel. Anyone? More comments? Robin and Rodolfo, I don't know if you want some remarks.
Yes, please go ahead, Rodolfo. Okay.
Thank you very much, Manuel, for your talk. I want to ask a question. Have you developed the ansatz for two electron systems, right? But as I understand, this is for closed shell systems. How do you go about for open shell systems?
Well, I only presented the expression for the closed shell systems, but obviously in our series we have actually open shell systems. So we have the expressions and they are very similar. You would have here the alpha alpha, alpha alpha plus beta beta, beta beta terms, and the exchange alpha beta and beta alpha. So in that case, you need to compute the single spin density functions as well as the density matrix of a single spin. And then you just sum the terms. I did not present them here because the expressions are very long and they are essentially a bit of a combination of these simple products. But in our program is considered if we are studying an open shell molecule, then we use the 2-electron open shell expression, which is slower to compute, but well, we have that. In fact, one of the things we need to use is, well, in that case, we are not always using the closed shell. We are using the correct 2-electron density. I did not present them here in the paper. In the appendix, we list the expressions.
Okay, for that, in that case, you will need a density matrix for each spin channel, right?
Yep. You can request to the programs that the wave function or the list of these coefficients, each atomic or the atomic orbital is molecular orbital is computed assuming that the orbital can have only one electron. In that case, you request the program, give me the decomposition using single spin molecular orbitals. And then they give you the list, and then you can split the alpha wave function plus the alpha beta part. And then you compute each term separately. And well, it's more work computational, but it is not that slow. It's maybe twice or three times the closed shell expressions.
Okay, have you thought of calculating in that case Shannon entropies for spin densities?
No, we haven't tried.
Well, it would be a good idea, no?
Okay, yeah. Thanks for the recommendation.
And then find out what happens with Shannon.
Right. But that would be a good idea because in open shell system you will have different number of electrons in each term, let's say. Yeah. Thanks for the recommendation.
In connection with what Alejandro was saying, right? About the limit of classical systems.
Possibly.
Classical contributions, right?
Yeah, very possibly. Yeah, I guess we could start from there. To what extent the entropies are very different as you are increasing the number of electrons, possibly.
Right. Thank you very much, Manuel.
No, on the contrary, thank you very much for the suggestion. We will really consider it.
Okay, so if we don't have more questions, we thank again our speaker, Manuel.
Sorry, Adrian.
Sorry. Yes, Robin. Yes. Oh.
Yeah, Adrian. I think there is a question in the chat.
In the chat, Humberto,
yeah.
You said, let me. It's here. Oh yes. So the question is about the software, the package you were using for calculations, Manuel.
For the wave functions, we use Gaussian 09.
Gaussian 09, okay.
Yep. From that package, we get these coefficients, and for the rest, we use our program is called Dense Toolkit. Oh, sorry, I guess I should have put the reference here, but you can search it in the web. It's Dense Toolkit, like in Density Toolkit.
Okay.
But the thing is, we have not released the program or the part that compute these properties. If you want to try it, just write to any of us and we can share a developer version. But it is not released, to be honest. We are kind of using it first before release it.
Okay.
Eventually we will release it, but right now it is not.
Okay.
Sorry. But I plan to release the numerical rules for integrating any function. So actually, if you have a program, you can just get the rules and then compute the function of the abscissas and then perform the numerical integration. So that would be published sooner than the release of the Dense Toolkit program. Yeah.
See, no, it's fair enough. Fair enough. Okay. Nice. So now we thank again Manuel, and the next month the speaker will be Ivan Gutierrez Sagredo from University of Burgos in Spain. So we hope everyone will be again with us next month, and thank you again, Manuel, for this very nice talk.
And the contrary, thanks to you, to all the organizers, and it's been a pleasure to speak, presenting the collective work. Thank you.
Thank you, Manuel.
Thank you.
See you soon.
Bye.
Bye.
Bye.